welcome to this webinar on an overview of optimization in OpticStudio. My name is Akash Arora, and I'm the product manager here at Zemax. I'll be your host for this webinar. Today we're going to talk about several things to do with optimization and optimization tools in OpticStudio. We'll start with the very basics, defining variables and merit functions in OpticStudio. We'll talk about the key capabilities, local and global optimization, and then we'll talk about a handful of handy tools that allow you to do things like manually adjust variables, find the best Asphere in your system, and also match off-the-shelf components to replace custom optics in your optical system. Following the live webinar, we will have a question and answer session. So let's go ahead and get started. First and foremost, in OpticStudio, optimization is the process whereby the program changes a series of defined variables in order to improve system performance. It's arguably the most valuable capability that the program offers. Variables can be any parameter in the lens data editor, the non-sequential component editor, or the multi-configuration editor. The merit function is a special editor where you define your targeted performance via a series of operands. Let's take a look at these basic capabilities inside of OpticStudio. Here's a sample system that I have open. And again, optimization has two key aspects that need to be defined, variables and a merit function. Here in the lens data editor, you can see several parameters have a V next to the cell. And if I click on that button, you'll see a solve status called variable. This is what allows the program to change that parameter during an optimization. Most parameters in the lens data editor, radius, thickness, material, various other terms like the conic constant and aspheric coefficients can be optimized. You can easily define a range of parameters as variables by clicking and highlighting and using the keyboard shortcut Control-Z to toggle variable status on and off. Alternately, here in the Optimize ribbon, which we'll be focusing a lot in this webinar, you have the ability to set all radii as variable, set all thicknesses as variable, or remove all variables in your system entirely. You also have these capabilities in the non-sequential component editor if you're designing an illumination system or a lighting system, as well as the multi-configuration editor if you're designing a zoom system or a scanning mirror system or something else that requires multiple configurations. Multi-configuration parameters can be variables as well. And in fact, that's one useful trick to optimize values which otherwise you would not be able to target. The multi-configuration editor allows you to call out values such as the system aperture, polarization state, and various other parameters. And that's a handy way to optimize values that otherwise you're unable to in OpticStudio. Once you've defined your variables, what you have to do then is create a merit function, which defines the target performance of the optical system. And that's what the merit function editor is for. If I open up the merit function editor, it opens up blank. And what's very handy is the optimization wizard that we have for defining merit functions like wavefront error, spot radius, or angular radius. You'll also see the ability to define boundary constraints on glass and air thicknesses to make sure that they stay in a manufacturable range. Once you click OK, the merit function will be defined for you. Each row represents a different target, and OpticStudio seeks during an optimization to make the computed value equal to the target for all rows in the merit function. What we're targeting here, as you can see, is RMS wavefront error. So the basics of optimization are setting up a merit function and defining your variables. The actual optimization process uses what we call local and global optimization, and those are the next topics that we'll discuss. Let's talk about local optimization first. Local optimization uses two algorithms, optionally one or the other, damped least squares and orthogonal descent. The choice of the algorithm is entirely up to the end user, and with local optimization, you give the program a starting point, and where the optimization algorithm ends, the result is a strong function of the starting point, and that's based upon the algorithms that we use. Damped least squares is the most commonly used algorithm. It's a derivative-based method, and it's really ideal for imaging and afocal systems. There's an alternate algorithm called orthogonal descent, and it does not use a derivative-based method. It uses discrete sampling to determine what direction to change the variables in order to improve the system performance. It's ideal for illumination and lighting systems or where the damped least squares algorithm stagnates. So any system where the derivatives are noisy or difficult to compute, orthogonal descent is going to be valuable in those types of systems. Let's take a look at how this works. So we've defined our merit function and allocated several variables here in this optical system. Local optimization is invoked using this optimize tool here in the optimize ribbon. And here you'll see the settings in the dialog, which were shown on the previous slide. The algorithm allows you to choose damped least squares or orthogonal descent. Typically, it's a good idea to start with damped least squares and only use orthogonal descent when necessary. In the cases where it works well, damped least squares is very fast. You'll also notice a setting to choose the number of cores. Optimization is fully multi-threaded, and in OpticStudio can use up to 64 cores in your machine, so it's very fast. Another thing that you'll notice is the ability to define a number of cycles. Oftentimes, leaving this at automatic is the most convenient option, whereby the optimizer will stop when it feels that it's no longer making progress. You have the ability to define some number of other cycles if you like. The other values reported here are the number of targets, so that would be the number of operands in the merit function that have a non-zero weighting, the number of variables defined, and then your initial merit function value. And as the optimization process proceeds, the current merit function value will, of course, change. You have the option to auto-update windows during the optimization process. This can be interesting, especially when you have layouts open for looking at the evolution of the shapes of the optical components during the optimization process. However, be cautious because if you have any analyses that require a long time to update, this can really bog down the optimizer. So I'll leave it off at this point. I'll go ahead and click Start here. And what you'll find is that this system is already quite well optimized. So it was able to make a little bit further progress, and it stopped with that value. If I exit out of here and update the system, you'll see that there were some slight changes made, but nothing significant. If you're starting with a basic system, flat pieces of glass, or adding additional surfaces, you'll find that optimization can make quite significant changes to your optical system. As I said before, damped least squares is really the best method to start with, especially for imaging in afocal systems. And because it's so easy to switch between damped least squares and orthogonal descent, you can easily choose one or the other if one of them is not giving the results that you would expect. There is a useful analysis for looking at the dependence of the merit function on a particular variable, and that is what we call the universal plot. We can look at a 1D or a 2D universal plot, and I will show that to you here. I'm going to look at a one-dimensional universal plot. And if I go into the settings, what you'll see is that the independent variable, the x-axis, can be any surface, system, or configuration value. So let's look at, say, the radius on a particular surface. In this system, we will look at, let's say, surface 6, for example, or rather, let's choose a different one, surface 3. We can select a range of values, say 35 to 37, with some number of steps. And we're just going to plot the value of the merit function. Alternately, we could plot any particular line in the merit function, and I'll go ahead and click OK. And you can see here, essentially, the optimum value for the radius on surface number 3. If I go to the lens data editor here, you'll see the value that OpticStudio chose after the optimization. It was about 36.5, which is right about the minimum of this plot here. So the universal plot can be a very valuable tool for looking at what solution space actually looks like. There's also a two-dimensional universal plot, which will show you a false color result, where the x and y axes are two separate independent variables, and a false color plot will show you the value of the merit function with a color representation. So these are some handy tools as you work your way through the optimization process for figuring out what is going on and where you are currently in solution space. So that was local optimization. Let's talk about global optimization. There are two global algorithms in OpticStudio. One is called Global Search and the other is called Hammer. These are two separate tools that we'll look at shortly in the Optimize ribbon. And these algorithms use what's called genetic competition, where they look at several different designs and those designs compete against one another and they retain the best or several best designs that have been found so far. Both of these algorithms will run until the user manually terminates them. And in any reasonably complex system, they're best left to run for long periods of time, hours or even days or longer. The difference between the algorithms is primarily in the scope of their search. Global search is intended for exploring solutions early on in the design process. So the scope of the search is very broad, and there's actually a strong random component to the search. So if you only run it for a short period of time, you're likely to get very random solutions. The longer you run global search, the more likely it is that the routine will close in on the best solution in the area of solution space where you reside. Global search also allows you the ability to keep some number of best solutions that have been found thus far. Hammer optimization is also a genetic competition algorithm. But the best way to think about Hammer is that the scope is much narrower, and the longer you let the Hammer optimizer run, the further away it will get from your starting point. So you can imagine it spiraling out from the starting point in solution space. Another very useful reason to use the hammer optimizer is that it can quickly get you out of a local minimum. With the local optimization routines, they stop when they get into a local minimum, where changing the values of variables by any amount results in an increase in the merit function value. The global optimization routines, because they continue running, will not have that same problem. And again, hammer is useful for getting out of local minima. Let's take a look at these two tools. We won't be able to look at a thorough running of these tools because they can take a very long time. So as I said before, they're two separate tools, Global Search and Hammer. If I open up the Global Search dialog, this is what you'll see. The global search routines also use the local routines. So once they find a promising solution, they'll use the local routines to get into a local minimum. They are also multi-threaded. And as you can see here, the global search routine allows you to save up to 100 of the best solutions. As you run it, it will show you the merit function value for the, in this case, 10 best solutions that it has found so far. As I said before, there's a strong random component if you only run for a short period of time, so global search isn't something that we can easily illustrate in a short period of time. What I will show you is the hammer optimizer, which is right next to it. The hammer optimizer, as you might imagine, also uses the local routines for the same reasons I showed previously, and is also multi-threaded up to 64 cores. The hammer routine is used so frequently that we've actually included a button to run an automatic number of local optimization cycles right here in the hammer dialog. So you can do both local optimization and hammer optimization here in the same dialog. As I said previously, hammer is very useful for getting out of local minima. And you'll be able to easily see that if you run hammer for several seconds and you see a sudden change in the current merit function. All of a sudden it'll drop to a lower value. That's an indication that you were in a local minimum. Now, I've run this hammer optimizer for about 20 seconds without any significant change, so I'm going to click the stop button. And it was able to make a very slight change, nothing that's in the significant digits of this merit function though. So we have reasonably good performance for the design solution that we have right now. So again, you've got your global search and your hammer optimizer. Another capability that I won't be getting into in detail in this webinar is glass substitution, the ability to optimize glasses. That capability is integrally linked to the global search and hammer tool. And you can find more information about that on our knowledge base, or we also talk in more detail about that in some of our training courses. Let's next talk about some of the various tools that we have for assisting with optimization. There are several tools that support manual adjustment, a couple of quick adjust tools, as well as a handy tool for manually adjusting variables and seeing what effect they have on the optical system. Let's take a look at each of these tools. You will find these tools also in the Optimize ribbon over in the Manual Adjustment section. The Quick Focus tool will quickly dial in the back focal distance, the thickness right before the image surface, and it will optimize for spot size or RMS wavefront error. The way that this works is behind the scenes, OpticStudio essentially sets up a merit function that will target the spot size or the wavefront error. It will remove all variables and only allocate the back focal distance as a variable and quickly optimize that value. And that's all done behind the scenes so that nothing here changes. Okay, and you can easily run that. If I click OK, you'll notice that just that value changed, just the back focal distance. The Quick Adjust tool is a very similar tool which will operate on any radius or thickness in your system. It also allows you to evaluate the spot size or the angular spot size for afocal systems on any surface in your system, not just the image surface. So it's similar to the Quick Focus tool, but allows you a couple of additional options there. The other two manual adjustment tools that I'd like to illustrate to you are the slider and the visual optimizer. The slider basically allows you, much like we looked at with the universal plot, to change any surface, system, or configuration value and essentially slide it while updating all the open windows. So if I wanted to see how the thickness of, let's say, the distance between the stop and the second group of lenses impacts things, I could change the thickness on surface 6. I can do a range of values, let's say from 10 all the way up to 15. And I can actually animate that. And you'll notice that the windows update as it moves through different values. And you can also change the delta value. You can see that it's changing in increments of tenths of a millimeter. Okay, and you can manually slide that as well. The visual optimizer does the same thing, but will show you all the variables currently defined in your optical system. And you can do that for multiple parameters at a time, not just a single parameter as the slider does. And I have another sample open, which does a really great job of illustrating the visual optimizer using lightning trace. So here I have lightning trace and the image of the spot for a point source at the focus of a parabolic mirror. If I open up the visual optimizer, and what I'm doing here is I'm changing the position of object 3, the detector. As I change that, you can see the effect of that on the spot. And actually, you're not seeing the effect of that. Let me quickly tell it to retrace lightning trace rays. And now you can see the effect on the spot as I drag that value around. So the visual optimizer is another handy tool for manually investigating how variables impact the performance of an optical system. Okay, there are two additional tools that I'll talk about very quickly here. The Find Best Asphere tool is really valuable and widely used by a lot of optical designers. It automates the process of figuring out which surface in your system would benefit the performance of the system most by turning it into an Asphere. And you can see the dialog here. You have the ability to search over any range of surfaces in your system. You have the ability to select what order Asphere do you want to add. And what the program will do is it will, behind the scenes, turn each surface in its own turn into an Asphere, optimize a predefined merit function that you've created, and tell you which surface produced the best merit function when turned into an Asphere. And this is a great way to save cost because, of course, aspherizing a surface both improves the performance of your system, but also typically increases cost. So knowing which surface would best benefit from an Asphere is a very valuable thing to have. That tool, and also the next one that I'm going to illustrate to you, can be found here in the optimization tools section of the Optimize ribbon. You'll find it here, Find Best Asphere. The last tool that I'm going to show you is the stock lens matching tool. The stock lens matching tool will automate the process of looking through the lens catalog and finding the best off-the-shelf matches for the lenses in your optical system. So what you can do is optimize your system to get the best performance, and you're going to have a series of custom lenses after that process. And then the tool will go through and iteratively swap in off-the-shelf components based upon matching the focal length, wavelength range, clear aperture, shape factor, and a host of other values. And it will tabulate the best replacements for each component in your system, and it will tell you how much that changed the performance of the system. So it's a very, very handy tool that will allow you to see if you can get away with using an off-the-shelf component without taking too big of a hit to the performance of your optical system. That tool as well is here in the optimization tools section. And as you can see here, you have the ability to select a range of components, a range of vendors, and you can also set a tolerance on how close the focal length and clear aperture of the stock component is to the component that you're attempting to replace. So this is a really handy tool that we added several releases ago. So that's really all of the key capabilities that I wanted to illustrate to you today. As you can see, optimization is a very important capability of OpticStudio, and it offers a wide range of tools and options for doing an optimization. We thank you for attending this webinar. The recording of this webinar should be posted to our website within a few days. If you have any questions or comments, feel free to email support@zemax.com and they'll get back to you as quickly as they can. For those of you that are attending this webinar live, we will start the question and answer session in just a few moments. Thanks very much.